Good morning, sir.
Yeah, good morning, sir.
Yes, sir. Now you are presenter, sir.
Fine, sir. Okay, sir.
Yeah, yeah.
Understood.
You can start session accordingly. You can wait 2 3 minutes more.
Sure, sir. Sure, sir. I'll
Yes.
wait for two, 3 minutes
Yeah,
and
yeah.
then start.
Yes. Yes.
Sure, sir. So, hello, good morning, everyone. Let me start the session. So, I'll start sharing my screen. Uh, Hope you are able to see my screen. Yes. Okay. So, the logic for today's session is we are going to understand the introduction to Intel SoC FPGAs. And earlier, we have done embedded system design using NIAS2 software processor. The objective of this session is to get introduced to embedded system using Cyclone 5 and ARM. And we are going to use the dual port RAM and perform the memory design and verification with respect to the signal trap logic analyzer, which is a debug tool. So let us start with this. When you say an SoC, we say it is an IC designed by stitching together multiple standalone VLSI designs to provide full functionality for an application. So, for example, when you say an SoC, we wanted everything to be IPs. They are intellectual property based, IP core based system on a chip design. So, in IC, in an SoC, what we say is an ASIC vendor may use a library of cores designed in house as well as some cores from fabless or chipless design houses, also known as intellectual property companies, which are called as IP companies. Okay, now what do we want in an SoC. That means when you see a system on a chip, that means you are transferring from system on a board to system on a chip. Then what logics we should understand? So let us understand that. Now, when you say the applications of SoC, the first application is, let us see, there is cell phone. But what is important in the cell phone is we wanted to ensure that it should operate at the very low power levels provided by the batteries. First, cell phone, very low power level. Telecommunications and networking, when you say, for example, you wanted to use telecommunication and networking equipment, then what is very important is we wanted to handle the huge data rates. That is also important. And third one, if you say digital televisions and set-top boxes, when you say, then we wanted to perform real-time video and audio decoding. So when you use cell phone, what is important is we wanted to operate at the very low power level provided by the batteries. That is number one. When you use telecommunications and networking, we need to handle huge data rates. And digital televisions and set-top boxes, if you use, then we need to perform real-time audio and video decoding. Okay. And when we use television production equipment, what is important for us? We wanted to ensure that it should operate at the extremely high computation rates. And when we use video games, what we wanted is we wanted to use several complex parallel processing machines to render gaming in real time. So if you see the characteristics in all the places, you can see in one place we wanted very low power level. In another place, we wanted to handle extremely huge data rates. So all those things need to be possible. If all these things need to be possible, then what is very important is we wanted everything to be present into a system on a chip. That's what in the earlier case we discussed, that system on a board to get into system on a chip. Okay. So let us explore that information and then we'll start doing the lab. So in the SoC design process, what is important is we need to choose the hard cores, then we should choose the soft cores, then we should add our user logic, and finally we generate the SoC design. This is the system on chip design process. And what is important is earlier FPGA was a separate chip, CPU was a separate chip, and DSP was a separate chip. We have seen that. But then now what happens? Let us understand that. We wanted to reduce the cost, right? And then you will have multiple informations. You need to ensure that the design is complex. But what is important is we have to reduce the power. So now we wanted the CPU capabilities inside the FPGA, and the same FPGA should take care of the DSP logics. That means, as I mentioned earlier, you have the DSP blocks. How many number of multipliers and accumulate units that are available, right? So that also makes very important logic for us. So we wanted the CPU should go inside. That means we wanted the CPU to be inside the FPGA. And we want all the IO blocks to go inside the FPGA. And then we also wanted the DSP that goes inside the FPGA. That means we wanted to replace all the external devices with the programmable logic. In order to do that, what is important for us is we call this as a system on a programmable chip. That is called as SOPC, which is also known as programmable system on a chip. If we need to do that, we call that terminology as an SoC FPGA, which is known as system on a chip FPGA. So the SoC FPGA devices integrate both processor and FPGA architectures into a single device. When you say SoC FPGA, then what is the meaning? You have the processor also, and then you have FPGA also. When both are available in a single device, then we call that as an SoC FPGA. So why do we need to have both processor and FPGA on a single device? That's what we need to get convinced. If you need to bring both into one umbrella, what is the greatest advantage we are going to get? Integrating the high-level management functionality of processors and the stringent real-time operations. Okay, we need to do real-time operations. In the previous slides, I showed you that when you want an SoC, we wanted to perform real-time operations. Second, extreme data processing. We need to handle the huge data rates. For example, you can see in Agilex devices, you can go up to 116 Gbps, gigabits per second. And then our interface functions. That means we need to connect multiple components and then generate a specific logic into a single device that forms an even more powerful embedded computing platform. So when you integrate all these things, then we are going to get a more powerful embedded computing platform. That's what is very important. And what is another important thing that need to be taken care here is, consequently, they provide higher integration. So when you add multiple components, that gives you higher integration. One. Second, it is lower power because it operates at a lower power, and smaller board size because since the system on a board is changed into a system on a chip, so it takes a smaller board size, and higher bandwidth communication between the processor and the FPGA because it ensures that you will have good bandwidth communication between the processor and FPGA. And they also include rich set of peripherals. So what are the things we should note down? When we club processor and FPGA into a single chip, what are the advantages we get? We get higher integration, number one. Number two, lower power. Number three, smaller board size. Four, higher bandwidth communication between the processor and FPGA. And what is also important is they also include rich set of peripherals because you have peripherals on the FPGA side. You also have peripherals on the processor side. So you have more number of peripherals, and you also have an on-chip memory, and then you also have a FPGA style logic array, and then you also have high-speed transceivers. That's what I was discussing about. The high-speed transceivers, you can operate in terms of gigabits per second. Okay, earlier it was 58. Now we can go up to 116. Right. Now, what is our focus today is to generate an embedded system design using the hard processor. Whereas in the earlier case, we developed the design using the soft core processor based embedded system. So now what we wanted is we need to ensure that it is a hardcore processor based embedded system. When you are trying to do that hard processor based embedded system, what is the meaning is hard processors are implemented in the fixed silicon logic of the SoC FPGA, similar to the serial transceivers. When you say hard processors are implemented in the fixed silicon logic, that means you can see that they are immersed inside the FPGA fabric. Okay, so then what is important is why we use hard processors. When you say hard processors offer higher CPU performance than soft core processors. So when compared to NIAS to soft core processor based embedded system design, we can get more performance with the hard processors. That's what we are saying it. And what is another important thing is you can see that all FPGAs are not SoC FPGAs. You can see some family of FPGAs are SoC FPGAs. So what is important is you have Agilex, you have Stratix, you have Aria, then Cyclone. So the max device which we discussed earlier is not an SoC FPGA. So the SoC FPGA starts from Cyclone devices, then Aria, then Stratix, as well as the Agilex devices. Now, when we say soft core processor based embedded system design, what are the things we should note down here is the performance and the cost are typically lower than in hard processors. When compared to hard processors, the performance and cost will be typically lower in the soft core processors, okay, when compared to hard. So this information also we know right now. And why do we need to use FPGA based embedded system design? That means the idea is, why do you want to use FPGAs for performing high speed embedded computing platform? What is the greatest advantage of using FPGAs for embedded systems? When you say the first important advantage is the IO peripheral, right? IO and peripheral expansion, because you have more number of input outputs that is available on the FPGA side. You have more IOs on the processor side. So you will have more number of system, right? You need to ensure that you have more number of Ethernet, general purpose IO ports, UART ports. So you will have UART that is available on the processor side. You will be having UART that is available on the FPGA side. You will be having Ethernet that is available on the FPGA side. You will be having Ethernet that is available on the processor side. You can also use general purpose IOs. There are multiple things. You can increase the number of IO channels by selecting those peripherals and configure a system. The second important advantage is when you use FPGAs, they can act as a co-processor, right? So your processor will be the processor, that is a master, and whereas your FPGA can act as a co-processor. So in applications where we require compute intensive algorithms, then in that case we can use FPGA as a co-processing element, because it is required in applications like signal processing, image processing, and packet processing applications. So in that case, what is very important is performance. If you want higher performance, then it is always better to go and use this, right, FPGA as a co-processor. Then custom embedded controller. That means you can decide how many processors you want, how many peripherals you want, how many interfaces you want, and how many DMA channels you want, that you can configure them together, and then you can include a custom embedded controller. That is also possible. And the last one is the multiprocessor, because your design will have multiple CPUs. In that case, what is the greatest advantage is you can improve the code reliability, you can increase the maintainability, and you can distribute all the tasks across several CPUs. So the greatest advantage is you can design a multiprocessor system as a custom inside, right? Custom system inside the single FPGA, or to augment an external CPU, because you don't require an external CPU. You don't require an external digital signal processor, because inside the FPGA itself you have a digital signal processor, and also you have a general purpose CPU. So you don't need to use an external CPU to develop an embedded system. You can use everything internally. That's the greatest advantage. Okay, to do this, what are the benefits? Okay, we have everything. That means we have FPGA, we have the processor, which is hardcore, and then we also have the softcore processor, right? You have everything combined together into a single chip. What is the advantage? Earlier, FPGA was a separate chip, CPU was a separate chip. Now what we are doing, it becomes FPGA plus CPU. Both are present into the same chip. The greatest advantage is increased system performance. Second, reduced power consumption. Third, reduced board size. Fourth, reduced system cost. So these things are very important for us to note down. Increased system performance. That means the performance is definitely increasing, no doubt. Reduced power consumption, because it is system on a board to system on a chip. Therefore, the board gets reduced. So power consumption is also lesser. That's what it shows here. It add-ons here. Reduced board size and reduced system cost, because you have lower component cost and reduction in the PCB complexity and cost. That is the greatest advantage. Why do we need to go for this SOC based logic? Okay, now what are the other important informations that we should know before we start working on a lab? When you say an SOC FPGA, that is nothing but ARM plus FPGA equal to SOC FPGA. A system on a chip FPGA is nothing but it is the combination of ARM, that is in Cyclone and in ARIA devices, you have a dual core ARM Cortex A9, whereas in Stratix and Agilex devices, you have quad core application processor A53 that is available. So now what you can see is the Intel SoC FPGAs provide the best of both worlds. That's what we say. It is nothing but ARM Cortex processor plus Intel FPGA. Both you can take it. Okay, now in the SoC FPGA portfolio, you can see that what and all are available as an SoC FPGA. So this slide is heavily populated, but it is very important that each and every information is necessary for us to understand the SoC FPGAs. If you see the Cyclone 5 and ARIA 5, you can see that whenever you wanted to go for lower power, and then you need to achieve higher performance. When you want higher performance, then you need to go to these devices. And you call this as low-end SoCs. This is mid-range. And then you have high-end SoCs. So when it is high-end system on a chip, then what is important is you will get highest performance and system bandwidth. When it is mid-range, then you use ARIA 10 and ARIA 5, which is again 20 nanometer. And low end, you can have 28 nanometer, which is Cyclone 5 and ARIA 5. So as of now, you can just say Cyclone 5 device, which we are discussing, which is 28 nanometer, ARIA 10, which is 20 nanometer, Stratix 10, which is 14 nanometer, and Agilex, which is 10 nanometer. Okay, as I mentioned earlier, you can also see that the Stratix and Agilex device uses a 64-bit. Okay, so you can see that this particular Stratix and Agilex uses a quad-core application processor A53 that was mentioned, which is 64-bit. Okay, and as I mentioned, you can go up to 116 gig transceivers. And one small example we can see here, it has a dual-core ARM Cortex A9, which can operate at 925 megahertz, whereas you can see the same operates at 1.5 gigahertz when it is a ARIA 10 device. So you can see that what is the performance. So if you want highest performance with the dual core ARM Cortex A9, you can achieve that with the ARIA 10 device, which is not possible with the soft core processor based embedded system design. So now you have 925 megahertz, 1.05 gigahertz, and then 1.5 gigahertz that is available here. Okay, what are the things that need to be noted down along with this when you say this is having a general purpose CPU? That is correct. It is an FPGA. Definitely it will have logic elements, that is adaptive logic modules. Okay, it will have memory resources, that is fine. But when we were expanding the diagram, we had FPGA which has the CPU, which hosts the CPU inside. That makes sense because that CPU operates at 925 megahertz, 1.05 gigahertz, 1.5 gigahertz, that is fine. But it also have a digital signal processor inside. That means it has a multiplier and an accumulate unit. So how many multipliers are there? That's what we wanted to have a look. So that will help you that how we can perform efficient digital signal processing inside FPGA. One small case if you take, this Cyclone 5 has up to 224 multipliers. Whereas when you compare the same with Agilex, you can go up to 17,056 multipliers. 18 cross 19. Same 18 cross 19, you can have only 224. And now you can see 17,056. Is the point very clear? Now you can see that how much it is bigger. We can easily come to a conclusion. Okay, now what is important for us is like we also need to have more number of multipliers inside. So DSP capabilities are available. It is already an FPGA, therefore you can see it has 2700 kilo logic elements. And then it also uses single precision half precision G flops. They are available. And it has a 64-bit, right? A53 MP core. Right. So when we need to develop this SoC design, so what is important is we need to understand the flow. That's the lab exercise we are going to see now. How that is going to get started. First, I will explain the typical design flow. When you take the typical design flow, what is important is we will start from the platform designer. We will create or open a platform designer system. We will add or configure the HPS IP. Here it is, HPS stands for hard processor system. We will open a platform designer system and then we configure the HPS. Then we will also configure some other IPs which are available in the system. Then we will connect all the components one by one. Then we generate the system. So you create or open the system. You will add or configure the IP. Then you will add or configure other IPs in the system. Then you will connect the components. You generate the system. After we do all these things, then what we will do, these things will be done in the platform designer. Then we will take this information to the quarters. So where we perform analysis and elaboration, then we do compilation. That's what we are going to see now. So let us start with the typical create project example first. Then I will also show you how that could be possible with a reference design example, where we can perform each and every step like analysis and elaboration. We do synthesis and we can go through the report. Then we can check what happens during fitter. Then we can also see the timing analysis, where how many clocks are there, whether the design is meeting timing or not. Those informations we'll see. So that will give you a background for us to enter into timing analysis in detail later. Okay, this is the typical design flow. To understand this typical design flow, let us start a design with the HPS system. Okay, right. Now let me open the quarters. So when we open the quarters system, I say here new project wizard, and then I say C drive and say IETE, and then I say system on a chip. So this is SOC design. Okay, and here notice the name of this project is system on a chip design. Now you can say next. So click yes. It is an empty project. Okay, click next. No need to add any files. We can click next. But this place is very important. As we know that you have Cyclone 5, ARIA, Stratix, and Agilex. When you see the Cyclone 5 family, how do we know this is an SOC device? That's what we should understand. When we expand this family of devices, and then if you scroll and then go to the end, you can see HPS CPU cores. For some of them, it shows 0. That means for some family of devices, they are still FPGAs. They are not SOC FPGAs. Therefore, they don't contain an hard processing system, CPU cores. If you scroll down right and then find out some devices, there are some places you can see HPU, CPUs cores, you can see 2. In some places, you can see 1. In one place, it shows single core. In some places, it shows dual core. So what is very important for us is before we start generating the system, we need to select the device correctly. That's what we are trying to do here. When we need to try to find the device correctly, so we need to ensure that which family we are doing. How do we know? When you say this SX family, which stands with S means SOC. SX, SE, ST, all these are SOC families. When it is GX or GT, they are the devices with the transceivers, okay, which is only FPGA. So now what we can do is in the name filter, we can try the Cyclone 5. So 5C. Okay, you can see that it is selecting a specific device. Okay, now we have selected something. So it is telling that you have to select the other device. So 5C, SE, MA5, right? F31C6. Now you can see that I have selected a Cyclone 5 device. It has 32,070 adaptive logic modules. And then if you scroll to the end, you can see that it has how many CPU cores. You can see that it uses 2 CPU cores. HPS CPU cores, you can see 2. So what is the device I have selected? 5C, SC, MA5, F31C6. So you can say next. Okay. There is nothing you can do that in the EDA tool settings. We can say next. And then in the project directory, we can see what is the project directory and then the project name, the top level design entity, all those informations are provided. We can just say finish. Okay, now we can open the platform designer. So tools and then open the platform designer. So instead of typing the NIAS to soft code processor, we need to type the HPS here to create the system. Okay, now you can see this is the platform designer system. And I am typing here HPS, which is hard processor system. When I type this HPS, you can see here ARIA 5 or Cyclone 5 hard processor system. You can able to see that. So you can click that. So in the hard processor system, you can see that on the left hand side, the signals which says H2F, that means it is HPS to FPGA. When it is F2H, that means it is FPGA to HPS. Similarly, you can see F2H, F2H, H2F. You can see that, okay, they are belonging to FPGA to HPS category or HPS to FPGA category. Communication between FPGA and the processor or the communication between the processor and the FPGA. So we can click finish. And the moment you click finish, you can see there are multiple errors. So what we need to do is we knew that whenever you add a component to the platform designer, we need to connect the corresponding clock signals, which are very, very important. Okay, now you can see what is the fundamental difference when you say earlier when we were trying the system with the NIAS, it was an Avalon memory mapped master that will be connected to the Avalon memory mapped slave. But then now you can see it is called as an AXI master, right? Because this is an advanced extensible interface because this is from the ARM, which is AMBA. Now what we need to connect is, it is showing that you need to connect the clock. So what we need to do here is first we need to connect the clock. So what it shows is the SDRAM clock must be connected to the clock output. So first we will connect the clock. Okay, you can see that one error is removed. You can see 3 errors. Second, you have an AXI clock that need to be connected to the clock. So you connect that AXI also. Then you have a F2H. This is FPGA to HPS AXI clock. That need to be connected to the master. So that also you connect. Similarly, the last one, right? The lightweight AXI clock must be connected to the clock output. So that also will connect. So you can see that when all these connections, right, with respect to these clocks need to be connected to the top level clock. So all the signals, clocks, we connected to the top level clock. Therefore, we can see that there is no error. Now let us add one component, on-chip memory. When you add on-chip memory here, you can just open it. And this on-chip memory is single port. If you want dual port, then you can click this dual port access, where you can see 2 clocks, 2 resets, and 2 slave signals. Since we want only single clock, we can just keep this as clock 1, S1, reset 1. So just to say finish. Now what will happen? You will have the on-chip memory connected with the system. But what is very important for you to understand is, this is Avalon memory mapped slave. Whereas in the master, it is advanced extensible interface. So the Avalon memory mapped slave need to be connected to the AXI master. That's what is important now. How are we going to connect this slave to the AXI slave? So how that process is going to happen, let us identify that. Before that, you can see there are 2 errors. One error is related to the clock. Another error is related to the reset. So connect the clock to the main clock. So this error is removed. Similarly, connect the reset to the main reset. So you connected that reset. So done. So this is clock reset that is connected. Second, what is important is we need to connect this Avalon memory mapped slave to the axis slave. So how do we connect this? Click this, so that this Avalon memory mapped slave need to be connected to the axis master. So this is Avalon memory mapped slave, but that is connected to the axis master. So here it is axis, but here it is Avalon, right? Both are connected now. Similarly, this S1 need to be connected to the axis master. So H2F, HPS to FPGA axis master, and H2F, that is HPS to FPGA lightweight axis master, because this is only 32-bit. Okay, your on-chip memory size is 32-bit. So it is connected to the lightweight. Otherwise, it will be 64 bits. So the lightweight is only 32 bits. That's what it is connected. To get more details, what we can do is you can expand this HPS. When we expand this HPS, right, we can see that FPGA to HPS interface width is 64-bit. HPS to FPGA interface width is 64-bit. Whereas lightweight HPS to FPGA interface width is 32-bit. That's what you could see, that the lightweight HPS to FPGA width, if you see, that is only 32-bit. Since this slave signal on-chip memory is only 32-bit, that is connected to this. That's what is specified here. Okay, so that's what is the basic meaning. If you want, we can get more details here. Okay, now what we have connected, we connected the HPS, which is the master, and then we connected an on-chip memory. Okay, we want to connect one more device. Okay, you can just connect that one more device here. Let us take one slave device, for example, JTAG you want. To connect the slave device, okay, when you connect a slave device, you can still see there are some errors. What are these errors? When you say, you can go to the system contents and connect the logics. You can see clock need to be connected, then reset need to be connected. And what is important is Avalon JTAG slave need to be connected to the master. So connect that. So the Avalon JTAG slave, memory mapped slave, is connected to the axis master, right? So that you can connect it. When you connect these pins, you can see there are some errors. Since the same platform designer is used for NIOS as well as for the SoC FPGA, the error is familiar with us. What is the error? When you say it is performing memory overlapping. So whenever that memory overlapping error comes, then what we will do is we will tell the tool to assign the base address. So in that case, we can go to system and say assign base address. When you say system and then assign base address, you could see that all these errors are removed. That's what we are seeing. So once these errors are removed, then we can generate the HDL. So when you click generate HDL, you can see it is generating the simulation files. It will also generate the synthesis files. We can click generate and then continue. Click save, so that you can save this. So I just say test and then we can save it. Okay, we can close this so that it can complete the task. Okay, so it will take some few minutes to complete the process. And once it is done, we can close the tab and then we can go back to the Quartus main window and then we can check whether that QSys file can be added. and then we will go ahead and do a reference design now. So we can click close and we can minimize the platform designer window. Come back to quarters, go to project, add or remove files in project, and then you can click this place. You can see a QSys file. You can say open. So this QSys file is added to your design. You can see that this is the QSys system file. So we can add this to our design. And when you open the main window and go to files, you can see the test.qsys is added in the main window. Okay, where are the reference designs for this SOC when you say, let us explore that. Okay, so I'll close this quarters and then let us again open it whenever required. So when we search into the right, the Terasic site, okay, when we enter into Terasic, you can see in the products, you have to select the SOC platform because what we are working is a system on a chip. So in the Terasic site, we should open the SOC platform. And what is the device we are working is the Cyclone. So you can directly go into the Cyclone page where you can see there is a board called DE1 SOC. So this is the board. So when you click this DE1 SOC board, which takes you to a page where you could see this device has FPGA as well as it has a dual core ARM Cortex A9. Both are present. And what is the advantage of this particular board? Okay, you can also see that, and these comparisons of this board with other third-party vendors, that is also available here. So you can easily get a comparison. What is available, what is not available. Those informations are here. Okay. Now, what is important for us to do here when you say, when you see the specifications, okay, you can get the details of this board, like what and all are available. So what is important for us to note down is, it is having a Cyclone 5 device. This is what you can remember, that this is the device filter I gave. 5C SEMA5 F31C6. And it has a dual core ARM Cortex A9. And you can see 85K programmable logic elements. Whereas our Max 10 is having 50K. This has 85K programmable logic elements. Okay, and then you can also see it has a dual core ARM Cortex A9. So therefore, how the structure will look like is, this is on the FPGA side and this is on the HPS side. On the HPS side, you can see there is a micro SD card. There is a 1 GB Ethernet, and then you have USB, and then you have UART, right? This is USB hub, and this is UART. Then you have a DDR3 SDRAM, which is again 1 GB, and then you have an accelerometer, right? And then you have LTC header. All these things are available on the HPS side. And then you can also use an user button, reset switch, one user LED. These things are available on the HPS side. If you see on the FPGA side, okay, you can see there is a 64 MB SDRAM. That's the lab we are going to do now. Okay, you have a 64 MB SDRAM, and then you have a video DAC. We have a video decoder. And what is important is, we have already seen the other things, like you have an ADC that is available here. And you also have, there are 10 switches. There are 10 LEDs. Then there are 6 hexadecimal displays. And then you have 4 keys, key IOs, that those things are available. So 4 keys, 10 switches, 10 LEDs, and 6 hexadecimal displays. These things are available on the FPGA side, and these things are available on the HPS side. So both are available on a single chip. That's what we call that as a system on a chip. Okay, now what is important for us to note down is, where do we get the reference designs? You can click here, resources. This resources will take you to the manual first. This is DE1 SOC user manual. So this is what first we should download. There are multiple revisions. It is always better to do the latest revision. For example, this is something, this is frequently asked question. But when you see the latest revision is this, that's what we can download. Okay, so this is the 2019, they downloaded. The other one is, you will have a CD-ROM, the DE1 SOC CD-ROM. This CD-ROM has the reference design examples for FPGA, reference designs examples for only SoC, that means only on the processor side. There will be reference designs examples for both FPGA as well as processor. How do we get the detail? For example, if you click this, it is downloading a user manual. I will explain that with the help of that manual. The moment I open this D1 SoC user manual, you can see, as I mentioned earlier, you will have the examples related to FPGA, examples for FPGA. So examples for FPGA, when you say, here you are going to use examples only related to FPGA side. We are not going to touch the processor side. For that, you have examples related to SDRAM test in Verilog, SDRAM test in NIAS2. There are so many examples that are available here. This is examples for FPGA. Then these are the examples for HPS SoC. That means this uses examples only on the processor side, and examples of both using HPS SoC, that means the processor as well as the FPGA. There is a spelling mistake here. You can see this is FPGA. So it has examples related to both FPGA as well as the processor. So you can see there are 5 to 6 examples for only FPGA. There are examples related to only processor, 3, 4 examples. And there are 3 examples which includes both FPGA as well as the processor. So that's what one example we are going to take here, and then complete the hardware design. That's our logic now. Okay, what we can do is you can download this D1 SoC CD-ROM. This D1 SoC CD-ROM, once we download, it will have all the reference design examples that are related to this board. Okay, we should have this D1 SoC user manual handy. Along with that, we should have this specific page. So this information will be very important for us because you have multiple examples which are related to the SoC. Okay. Now, one such example which we have downloaded, that's what we are going to see now. So for doing that example, again, let us revisit the typical design flow. We will open the platform designer window, which already have some specific logic. We will modify some of the components. That means we'll just change something, and we want to add something, we want to remove something. That we can do with the existing QCs. Then we will do synthesis. Then we will generate a fitter. We will generate the programming file. So what is the only difference is, when we are trying to do the same steps which we did that with NIAS2, it was showing only the FPGA resources, because you built the processor with the resources which are present inside the FPGA. Whereas this is quite different, because you will have the processor and its own peripherals will be there. So in the fitter report, we can see that which are the components that are used in the FPGA section. We can also see what components are used in the processor section. So you will have a fitter report which distinguishes between what components are there on the FPGA side and what components are there on the processor side. So that information we can see. That is very critically important for us. Okay, right. Let us start that design. So I'll open the folder, and you have a specific example. So let us start with that specific example. Let me open that folder also to understand that. Okay, where is that folder? How that could be working out, I'll show you. If you open this D1 SoC CD-ROM, this CD-ROM, whichever I have downloaded, you will be having a folder called demonstrations. Inside the demonstrations folder, you will be having 3 subblocks, right? 3 subfolders. One is called FPGA. It will have examples only related to FPGA. Okay. Then you will have another folder called SoC. It will have examples only related to the HPS side, that is hard processing system side. Then the third one is SoC FPGA, right? These examples are related to both processor as well as FPGA. So in this only we are going to take one example now. My first HPS FPGA is the example which we are going to take now. So I will just copy this example from here, that means this folder, and go to C drive, create a new folder so that we can start from scratch. So new folder and SOC design system. Okay, inside the SOC design system, I will paste this my first HPS FPGA. Okay, so I have created a new folder called SOC design system. Inside that SOC design system, the available reference design is placed. Okay, let us start the project now. So open Quartus, go to open project and go to C drive and click here SOC design system. So when you say SOC design system, okay, let us find out what is that SOC design system. So let us identify, right? So this is the folder and go to my first HPS FPGA. Inside that you have to select the SOC system.qpf, which is called as the Quartus project file. So select that and we say open. Okay, now you can see that whenever we open a project, right, which is created in some version and you are trying to open that in another version, we need to upgrade the IP, right? We need to upgrade the IP. So therefore, you can see for this, when we bring this example, right, it shows that very clearly down. This was generated in some version and you are trying to open that in another version. So therefore, we need to upgrade the IP. So we should click here, launch IP upgrade tool. Whenever you click launch IP upgrade tool, it will request us so that we need to ensure that the IPs should be upgraded. So for that, what is the option is, we have to click here, perform automatic upgrade. When we click perform automatic upgrade, you can see on the right hand side it is showing regenerating. That means all the IPs are getting upgraded. They are regenerating. Once they are regenerated and successful, then we can proceed further. Okay, it will take few minutes. Okay, so during that time, what we can discuss is we can open the lab and see what are the important points that need to be noted down. When we do the lab, the first thing what you should understand is the one which I explained. Whenever you create a reference design example for an SOC FPGA, we have to choose an SOC device as the target. That is very important. If you are choosing an SOC device as the target, then the Cyclone 5 SE, that means you can see that all S families are SOC devices. So Cyclone 5 SE, Cyclone 5 SX, Cyclone 5 ST, similarly ARIA 5 SX and ST, ARIA 10 SX, and Intel Stratix 10 SX. Okay, all these things are SOC devices. And they also say some Intel Stratix 10 MX FPGAs are also SOC FPGAs. As I mentioned, you have to drag and see that whether the HPS CPU cores are mentioned some numbers, either 1 or 2, it should not be 0. If you have selected a device which is 0, that means those are not SOC FPGA devices. Okay, this is very important point to note down. The second important thing is, whenever we use a platform designer system integration tool, the greatest advantage is it is a GUI based system integration tool. Therefore, it is very easy for us to click the system design. And it simplifies the complex system development. It automatically generates the interconnect among various off-the-shelf and custom IPs. And it provides a standard platform for IP integration, custom IP authoring, IP verification. So all those things it will take care, and it also enables the design reuse. That is very, very important for us. That's what we can reuse the same design. That's what we are doing now. We are opening the design which is already created, and whatever things we want to add, we can remove those things we can do, and then we can make that as a custom logic. Okay, let us go back to the design now. Okay, it is still running. Let us complete it. Let us wait for a minute to ensure that it gets completed. You can see it is 5% because it has to upgrade all the intellectual properties to this standard. That's what it takes time. Okay, now you can see that device family Cyclone 5 and regeneration status, it shows success. Okay, so it is done now. So we can click here, close. Then what we should do is we should go to tools and then we should open platform designer because we wanted to see what is present in the existing design. In the existing design, what is available, then we can want to modify something, we can do it. So just open that existing design. You know that the existing design will be having the extension .qsys, okay, which is the Quartus system integration file. You can just open it. Now you can see this system has an HPS, which is the hard processor system. It has a PIO LED, which has SysID. It has on-chip memory. You can see there is an on-chip memory. What is important is the on-chip memory has an Avalon memory mapped slave that need to be connected to the master. You can see that is connected to the Axie master, like what we connected last time. There is a JTAG UART. You can remember we brought this JTAG UART also. This clock reset, Avalon, JTAG, all these things we have connected. Okay, so what you can do is you can connect this HPS, PIO LED, HPS SysID Q6. Then you can connect, right? So all these things, whichever we require, that we can export it accordingly. Okay, once we bring this together, we are going to generate a system. Okay, let us open this and see here. This is FPGA interfaces. If you go through the FPGA interfaces, as I mentioned, you can see all the interfaces here. Second thing is you can click peripheral pins, which will tell you which devices, that means which peripherals are enabled on the HPS side and which peripherals are unused, that we can see. Which peripherals are used and which peripherals are unused, that you can see here. See one example, Ethernet media access controllers, which is Ethernet MAC. You can see that the 0 pin is unused, whereas the first pin is used. It is set to what you can see. Whereas the NAND flash controller is unused. Quad SPI flash controller, it is used. And USB controllers are unused. SPI controllers, in that one is unused, the other one is used. UART controller, one is used, UART 0, the other one is unused. In I2C, right, you can see the I2C 0 is used, I2C 1 is used, but I2C 2 and 3, they are unused. CAN controllers, both are unused, and this is what is the peripheral tab. So you can see that whichever peripherals are enabled, that information we can see where they are set to. And the third tab, which is important, is called as the HPS clocks. We know about the FPGA clock, but we also need to know what are the clocks that are available on the HPS side, the hard processor system side. You can see what is the input clocks and what is the output clock. If you click the input clock tabs, you can see what are the input clocks, and if you click the output clocks, you can see what are the clocks that are available on the input and output side. And the fourth one is the SDRAM, which is DDR3 protocol. What is the memory clock frequency? Is 400 megahertz. That's what we have seen in the Cyclone 5 table. So the DDR operates at 400 megahertz. Okay, now what we can do is, we wanted to change some settings in this. For example, what I do is, we will just remove this interrupt. For example, I say remove this enable FPGA to HPS interrupt. So I just remove that. When I do this, you can see there is a lab. That means there is an error which shows that, okay, you have to ensure that we need to remove this dangling connections. So how we can remove this? You can go to system and say remove dangling connections, so that is removed. So once that is removed, now what we can do is we can start completing the logic. So we removed this. Then what we can do right now is we can generate the HDL. For example, you wanted to ensure that, okay, the design works. We have to generate the HDL because we modified something and we want to add something or remove something. Then we have to generate the HDL one more time. So now you can click generate HDL, click generate, and you can close the system. This is not going to ask you a name because there is already an existing QSys file and it is going to update the same file. So let it generate within a minute. Once we say that it is generated, we can go back to the quarters. So in the quarters, we can do step by step. First, we can do analysis and elaboration. Then we can do synthesis, and then we can see how many reports, how many 7 input, 6 input, 5 input it takes, and then how many lookup tables, how many flip-flops, all those informations. And then we can say how many number of memory blocks it takes on the processor side, means like on the FPGA side. All those things, let us check. Click close. Right, now what we can do is we can minimize this process, come back to the Quartus main window and perform analysis and elaboration. Okay, once it is performing analysis and elaboration, let us go through one slide again. So when you take this platform designer, we opened the tool and then it was showing HPS, which is the hard processor system. So what is important to note down is the HPS component. In the HPS component, whatever is showing F2H, that means it is FPGA to HPS. Whatever it is shown H to F, that is HPS to FPGA. So both informations we have seen. And another important thing to note down when you say, you will have multiple tabs, FPGA interfaces tab, HPS clocks tab, SDRAM, etc. All these tabs. So we can ensure that all these tabs we can cross verify. So you can see that whichever signals you want, you can see. This is a signal I mentioned. You can say H to F stands for HPS to FPGA, and then you can see that these are the signals. Similarly, on the right hand side, you can see which are the signals available here on the left as well as the right. This is F to H, this is H to F. Okay, there is an option called enable general purpose signals. When you enable that, you can see all the signals. In the earlier case, as I mentioned, that it has 3 master interface. You had both are 64-bit. The other one is the lightweight, which is 32-bit. So that is also explained here. So FPGA to HPS slave interface, HPS to FPGA Axi4 interface, lightweight HPS to FPGA master interface. When you say lightweight, it is 32-bit Axi. This is what is used in our design. And these are the bridges that are available in the Cyclone device. FPGA to HPS, that is the first one. HPS to FPGA, next. Lightweight HPS to FPGA, third. Then SDRAM interconnect. Okay, now let us move on to the platform designer and open the Quartus main window. Here you can see it shows 100%. Go to tools, netlist viewers, and go to RTL viewer. So you can see that this is your clock, okay, which is 50 megahertz. Then you can see there is an HPS that is connected. That's on the FPGA side. You can also see that what is available on the HPS side. If you drag this, you can see this is all HPS, hard processing system. When you click this SOC system, you can see how complex is that. Okay, now we can continue with the synthesis portion. So you can say analysis and synthesis and say start. When we do analysis and synthesis, what is our thought process is it should show the resources which are used, but then we can have logic elements. That means here in our case, this is adaptive logic modules. What is the fundamental difference when compared to the earlier scenario when you say that has been targeted for max 10 device? So therefore, what happened was we could see in terms of only logic elements, lookup tables. But here you can see in terms of ALMs, which is adaptive logic modules. Okay, because this has, right, in your earlier case, you had only 4 input lookup tables. But then the latest FPGAs has 8 input lookup tables, I told you. So let us see that now in detail. So it will take some time, a minute to complete this process. But when it is running, again, we can just go through one important slide. How do we start with that slide? I'll just show that information to you. First thing is the clock and reset. Let us start this. Whenever you use a clock and reset, there is an input clock that is available that is also having an output clock. That's what HPS clock and reset tab, if you click, you can see the input clocks as well as the output clocks. Both you can see. That's what is specified. Another important thing is when you click this pin mapping, you will come to know what are the resources that are available. That means what are the peripherals that are available. You can see here HPS quantity. HPS quantity means on the HPS side, how many are available. And this is the other block which is called as FPGA quantity. So that is important for us. So when you click that pin mux and peripherals, you will be getting that interface now. So with this, what we can do is how many are available on the HPS side, how many peripherals are available on the FPGA side, how many are used, that information we can see. For example, USB 2, and how many are used we can see. Okay, that information we can check. This is called as pin mux and peripherals tab. Okay, let us expand that. Okay, let us ensure that this completes, then we can have a look at it. Okay, meanwhile, let it's running. You can see that here. If you click this, right now, if you go through the system contents and then the address map and then the parameters, right, we can definitely have a look at that logic now. So on the FPGA interface side, let us go through the system contents again. Click that and go to peripheral pins. Okay, so here you could see what are the peripherals that are added. And here you can see the HPS clock. These are the input and output clocks which I mentioned. And then you can also see the STL. When you click these peripheral pins, and then you can see the details here. So all the peripherals, you can see the details. Ethernet, okay, NAND flash controller, quad SPI, USB controllers, SPI controllers, UART controllers, all these informations are available. That is available on the description side. So these informations are there, which we can definitely look into. So for example, if you go through this specific logic in the pin mux, we can get that information in detail. Okay, finally, what we are going to do after getting this pin mux, we need to instantiate the HPS in the platform designer. That's the step we are going to do that. That means we brought that to the quarters and then we are performing synthesis now. So when you open this process, right, let us see what happens in the synthesis logic. You can see that how long it takes to perform synthesis because it has a dual core ARM Cortex A9. Along with that, you have memory, you have other peripherals and IOs. Okay, so now you can see logic utilization in ALMs. You can see it shows not applicable. We will come to know the utilization of the adaptive logic modules only during fitter. Now, how many registers you can see? 3134 registers. And how many pins it has used, that also you can see. How many number of total memory block bits, that also we can see. We can expand analysis and synthesis and go to resource usage summary. So this is the place which I mentioned. Because in the earlier Max 10 device, we had only 4 input lookup table. So therefore we have seen how many 4 input, how many 3 input, and how many 2 input. But then here this is, you can see this is an adaptive lookup table where you can go for 7 input, 6 input, 5 input, 4 input, less than or equal to 3 input. You can see in all the places you have some number. So that clearly shows that you can have the lookup tables which are used for all the inputs here. And you can also see the memory bits, how many number of memory blocks that are used. To get more details, you have to click the RAM summary. When you click here RAM summary, you can see that how many single port RAMs are used and how many simple dual port RAMs are used. Dual port RAMs means you will have both port A and port B, both are used. Okay, that information also we can see. Okay, let us complete the fitter process and then we will also open the schematic. Okay, now at this junction we'll open the schematic. Tools, netlist viewer, technology map viewer, post mapping. So now this is the complexity of the system. For example, you open one specific logic cell. Okay, now you can see this logic cell has a specific property. You can see that, okay, how this is connected. All these informations we can see. Similarly, this is registered to that. Okay, this is the place where they are available. You can see that. What are the outputs? If you select this is 5 input, so this is only 3 input. You select 1, 2, 3, 4, 5, 6, right? You can select the 6 input lookup table. So we can scroll this here and select this entire lookup table. This is 6 input. So you can see the properties of that. You can see 1, 2, 3, 4, 5, 6. What are the ports that we can check here? Data A, B, C, D, E, F. And if you wanted to find out a larger logic element, that is also possible. We can go beyond and find out. Here you can see. Okay, and then you can see the flip-flops. That's a flip-flop. You have clock, you have D, and then you have NL. These are the registers. So this is during synthesis. We have seen the resource usage summary. We have also seen the RAM summary. Okay, now what we can do is we can do the fitter operations. Expand, fitter, and say placement and routing. When we do fitter, as I mentioned earlier, we will see two things. One is we are going to see the resources which are used on the FPGA side. We will also see the resources which are used on the HPS side. Both we can see. In the same fitter, we can have two partitions. And we can see the resources in the chip planner. And we can see netlist viewer. And then we can also see the viewer which is done after post routing. That is post fitting. Technology map viewer. Post fitting we can see. And we can also just click timing analysis and see whether the design meets timing also or not. So one by one, let us check. So let us give us a minute. So once it is 100 percentage, two three things we have to check, as I mentioned earlier. In the earlier case, it was not showing the number of adaptive logic modules. It shows still, you can see, not applicable. But then when the design gets fitted, we can see that. Okay, now you can see that there are 2214 logic elements, that means adaptive logic modules, and 3288 flip flops, and 360 pins are used out of 457, which is 81%, and the memory bits is 13%. No DSP blocks are used, but then we can see that. Okay, you can expand the fitter, go to resource section, and resource usage summary. So in the resource usage summary, what is important for us to note down is this: 7 input functions, 6 input functions, 5 input functions, 4 input functions, less than or equal to 3 input functions. All are available. Then we can also see the hard processor system peripheral utilization. Because in the earlier case, we have seen only the resources which are used on the FPGA side. But now you can see the resources which are used on the processor side. You can see there is a tab which says that hard processor system peripheral utilization. So you can see that which devices are used. For example, Axi lightweight, it is used 1 cross 1. SDRAM, that is used. Okay, but which is not used, we can see that. For example, SPI master, only one is used. We have also seen in UART, only one is used. You can see here, 1 by 2. USB also we see only one is used. So USB only one, 50%. UART there were two, only one. SPI we had two, nothing is used. Right? That is SPI slave. SPI master, it was two, only one is used. So like this we can see. So this is the resources which is used on the HPS side, because it is not going to use the resources which are present inside the FPGA. Okay, now we can open the chip planner. So go to tools, netlist viewers, right? And first we'll open technology map viewer post fitting. Post fitting means this is after fitting, placement and routing. So you can open this blocks, right? You can see that. This is your DDR and this is your logic cell count. So if you see the properties, okay, now you can see these are the things that are available, which are the ports, and these are the 5 bit. Okay, all these logic cells are there, and these are your flip flops. This is again internal register, and this is your logic cell. Okay, now what we can do is let us explore the chip planner. Go to tools, and then you can go to chip planner. So you can zoom this, and you can see these are the memory blocks that are used. Okay, all these are memory blocks. First, this is your hard processor system. You can see it has a flash controller, it has an ARM A9 subsystem, on-chip peripherals, PLLs, on-chip memory, DMA, all those things we can see. And we can also see the resources which are present on the FPGA side. Since it does not use any DSP blocks in this example, no DSP is selected. Okay. Whereas here you can see memory blocks are selected. Now, if you again open the report, we can see that how many number of memory blocks, that information we can see. So you can see total number of M10K memory blocks. One block is M, that is 10K. So therefore it is 68 it is using out of 397. There are 397 M10K blocks that are available in this device. Out of that, it has used 68. So 17 percentage are used. That's what it shows here. Okay, and these informations we can see. Okay, whether this has any FSM, that also we can see. Go to tools, netlist viewers, and then go to state machine viewer. You have to check whether the design has a state machine. You can see a state machine here. So there is an ST header. It has a read data, and then you can see at what condition it moves from one state to another state, and what is the encoding. That information also we can see. So that means in the all the viewers we have seen. See here the RTL viewer, technology map viewer post mapping, technology map viewer post fitting, state machine viewer. All the four we have seen. Okay, let us continue with the assembler. Then we generate the timing analysis. Go ahead with the assembler. Okay, right. Now we can see the timing analysis. Let us run the timing analysis tool also and check are there any violations, because this is not our design, it's a reference design. Let us see that whether design meets timing. Okay, then it is very easy for us to understand when we constrain the timing constraints for a design. You will come to know, okay, whether what reports to see. So let it open the timing analyzer. Let us see that. Okay, so once the design opens, how do we open this? Go to tools and you can open the timing analyzer. When we open the timing analyzer, on the left hand side you can see create timing netlist. We have to just click that, which generates the timing netlist for us. Okay, now you can see the clocks. How many clocks are there in this design? You can find out a tab called diagnostic here in the timing analyzer tool, and there you have to click report clocks. So when you click report clocks, here you can see that, okay, all these clocks are base clocks and these clocks are generated clocks. The clocks are generated from the base clocks. You can see there are multiple clocks that are available. And how do we know that the design is meeting timing? So for that, we can check, right? Are there any unconstrained path? That also we can see. There is a command called report unconstrained paths. You can see this many unconstrained clocks are available and unconstrained input ports, output ports are available. Okay, let us identify the timing report. So click report timing, and you wanted to know how many number of paths. For example, I want 20 worst paths. I can give a number. Otherwise, by default, it will always give only one path. Okay. So when you say report number of paths 20, then it is a setup path and say report time. You can see that. The setup slack is 1.730. That means the required time minus arrival time is a positive number. Okay, setup slack is positive. Okay, but then we also need to see the hold. Okay, before seeing hold, let us just understand the path which is critical path. Okay, when we need to analyze that path, okay, what is available in Quartus is you can, from the timing analyzer, you can do a cross probing. For example, you select this path and then you can go to locate path and locate in chip planner. If you say it will locate that in the chip planner, or you wanted to locate that in the technology map viewer, you can select that. So this is the path which it generates that is connected now. If you wanted to see those paths in the chip planner, then you can select. For example, I am selecting multiple paths. Okay, I am selecting all these paths, right, that need to be taken care. So all these paths you select, launch clock, everything you select. Okay, we wanted to see these paths and locate this in the chip planner. So you can see those paths that are available in the chip planner. So where these paths are starting, that information we can see that. Okay, so this is the information which you can get. So that means when you expand this and you can locate these 5 paths. So whichever arrival clock you want, that informations we can select here, which is the arrival clock. All these informations you can select. And then you can see them in the window. Okay, so these are informations could be seen now. You can see this path which are highlighted from this place to this place. Okay, all the paths you can highlight. These informations are also possible. This is one way. The second way is you wanted to see that in the resource editor. You can just say locate in resource property editor. So here also you could see that. Which path is that? Okay, we'll get more details about that when we do timing analysis in a specific class. But the information is if you open an SOC design, right, like performing functional simulation, checking the timing analysis is also an important task. Okay, when you wanted to see the worst paths, right, you wanted to see the slack histogram, that also can be possible. Reports, go to diagnostic reports and open create a slack histogram, which will ask for 1 clock. You can select whichever clock you want and say okay. You can see that. This is the number of slack value that is available on the x-axis, and the y-axis you have number of paths. Okay, if it is red, that means that paths are not meeting timing, right? But these are the worst paths. These are the critical paths. They are very near to 0. Okay, so this is what is the hardware design we have seen now for a system on a chip design. So that's the first lab which we have seen now. So what we have done in this lab is we have taken a reference design which is available in the Jurassic, right? And then we copied that design and created a new folder. And then we understood what is available in the platform designer. Then we integrated that to the Quartus and then we completed it. Right, now another example what we are going to see. I will explain the background of that example. After we instantiate this design into the platform designer, we will connect the components. That's what we did now. Either you can click the open dot to make a connection, or you can right click an interface to make eligible connection. You can also click that. Both are possible. Then we completed the system. When we complete the system, how do we generate this? We create the platform designer interconnect. It will generate the source file for synthesis as well as for simulation. Then we will generate the handoff files. This is what we have to do now. Okay, that's what is generated now. Okay, now let us do the next lab. In this next lab, what is planned? Okay, that also I will explain. Instead of doing that with the platform designer, we are going to generate a system which is completely based on the block. Okay, let us explore that in detail. Okay, so here this lab has what? Let us explore that in detail. This particular lab has a block in which you have a dual port RAM, which is a DP RAM. You have an up counter and then you have a down counter. In the up counter, you can see that you are going to use write address, and this down counter is for the read address. You have a write address, you have a read address. Now you have a ROM where there is a memory initialization file, MIF file is already available. And now what we are going to do is you have one block called up counter. This is again an IP core. A down counter, which is again an IP core. You have a DP RAM, which is available as an IP, RAM 2 port. That's what we are going to instantiate. You will have a ROM that is also taken. And then we also have a PL, which is a phase locked loop. So you have memory resources. You also have a clocking resource. You also have an IO resource. So all the resources we can see in this design. So you have a PLL which takes the 50 megahertz clock as the input. It takes the 50 megahertz clock as the input and it generates two clocks. One clock is 25 megahertz that is connected to the read clock and another one is connected to the write clock which is 75 megahertz. So it generates two clocks. One is 50 megahertz and the other one is called as the 75 megahertz. 25 and 75. 50 megahertz it takes and generates two clocks. 70 megahertz is connected to the write clock and 25 megahertz is connected to the read clock. And that is connected to the LEDs. Okay, this is the data out where we can see which data it is coming out. Now you have a down counter and then you have an adder. So there are 6 IP core blocks: up counter, down counter, DP RAM, adder, ROM, and then PLO. Using all these blocks, we need to generate a top level module. There is a test bench that is available, and using that test bench, we need to perform the compilation process. And finally, what we wanted to do is we wanted to implement the design and ensure that the design works fine. Okay, that means we need to debug it. To understand that process better, what we wanted to do is there is a reference file. That's what we are going to select. But before that, what information is very important is we also need to see the MIF file, which is called as the memory initialization file. In the memory initialization file, what is given is, right, now if you see this ROM from 0 to 63, first 63 locations, that's 64, the decimal is 322. That is what is stored. From 64 to 126, 66 is stored. And from 128 to 191, 323. Then from 192 to 255, 0. That's what we are going to verify. Is that working fine or not? How that MIF file is generated, you can see on the left hand side. Content 0 to 63 is 322. 64 to 126 is 66. And 128 to 191 is 323. And 192 to 255 is 0. Okay, now these are the 4 things. You can see width is 9, depth is 256. So therefore, while creating the IP, we have to change the width to 9. That means while configuring, we have to ensure that the width should be 9. Depth should be 256. Depth need to be changed to 256. Width should be changed to 9. That's what this we have to understand. Okay, let us continue with the process now. How do we continue with the step? So what is available? You already have a Quartus archive file. This file will be given to us as reference. We can take that file now because this file has all the IP cores generated except DPRAM. So let us copy this now and go to C drive, create a new folder and say memory design and verification. Just check whether it is correct. Memory design verification is the folder. Inside that folder, we paste this Quartus archive file. Now I'll open the Quartus. Click here, open project. Go to C drive and say memory design verification. That's what we wanted to check. So in the memory design verification, let us check that, whether that logic is available. Click that lab one, click open. And it is an archived project, so you should unarchive to see what files are available. So we have to launch the IP upgrade tool so that if any IPs need to be upgraded as per the specific version, that can be upgraded. We can wait for a minute to ensure that the IPs are upgraded. Okay, now we can click close. So let us open the top level module. For example, if you change this to files, you can see up down counter, up counter, down counter, PLL, adder, all these things are available, but except you have the DP RAM. That's what we should add. Okay, generally what we should do is we should add the IP right from the IP catalog. So what you should type here is on chip RAM, on chip memory. In the on chip memory, in this example, since already adder, PLL, up counter, down counter all are available and ROM is available as an MIF file. What we wanted is we need to add this RAM2 port. Just add RAM2 port. And the name of the RAM is DP RAM. That's what we are supposed to provide. So DP RAM, which is dual port RAM. Click OK. Once the Mega Wizard plugin manager opens, you have to see that this memory will have one read port, one write port. Correct. So you see the block diagram before saying yes or no. If this specific device has a read port, you can see there is one write port, there is one read port. That means you have read and write. There is a read clock, there is a write clock. Therefore, while selecting the parameter, you should say with one read port and one write port. You should not select with two read port and write port. Okay. Click next. How many bit 8-bit words of memory? So here you have to change this to 256. And here I told you the data width should be changed to 9. This is what we want. And click next. And do you want single clock or do you want two clock? That's what it's asking. What kind of clocking method do you want to use? That's what it shows. So what kind of clocking method means we don't want single clock. So therefore you should say dual clock. Use separate read and write. That is correct. That's what we want. Use separate read and write clocks. And then what we are supposed to say is click next. We don't need to add any other parameters like data, write address, write enable. All those things are available. So nothing we need to add. Click next now. We don't need to add any memory initialization file. So we can just say no, leave it blank. Click next. And you can generate the netlist. Click next. And you can add the instantiation file. Then finish. Okay, then once it comes to this place, you can click yes. That means you have added DPRAM to the Quartus project. You can see here DPRAM dot QIP that is added to the design. Now you can directly go ahead and perform analysis and elaboration. That's what we are going to do. After performing analysis and elaboration, we have to cross verify whether all the 6 blocks are exactly connected in the same way how it is specified in the lab manual. Okay, now you can say it shows 100%. Go to tools, netlist viewer, RTL. So now you can see all the 6 blocks. So you can see here DPRAM, which is the PLL, right? And then up counter, row, down counter, adder, DPRAM, all are available. So we can just open PLL, maximize that. And you can see there are two clocks. One clock is C0, another clock is C1. That means you can see one clock is connected to the right, another clock is connected to the read. That information we can see because it takes the clock, that is 50 megahertz clock as the input, and it generates two clocks. One is 75, other one is 25. So PLL is used. Then you can see up counter. Okay, then this is down counter, then adder, row, then DP. Now we need to verify the functionality by the help of a test bench. Okay, now what we need to do, as earlier, we knew that whenever we generate a test bench component, that means you have a simulation component. How do we go ahead with this logic? Let us explore that now. So go to tools, run simulation tool, RTL simulations. Before doing that, what is important is we have to check where the test bench is set. Okay, go to tools and say options. Okay, and then you can click here EDA tool options and say that whether the path is set. Second thing what you should check is tools. Okay, and go to assignments, settings, simulation settings. Here you can see that the test bench is already set, TB underscore DPRAM. So directly we can generate. So go to tools, run simulation tool, RTL simulation. We will run the simulation and see what happens. We'll open model sim. Okay, now we can say do wave dot. So you can see the waveform. Let us see the clock here one by one. Okay, let us explore the clocks. So we'll zoom this, and you can see there are two clocks, okay? And we can see the values here. So let us check that in each and every things. What is the value? And this is the Q value that we can drag it here, and this specific value we can change this radix into decimal. Okay, so that you can see the values are same. This Q and this should be providing the same output. Okay, so this is 113, this is also 113, this is 112, 112, 111, 111, 110, 110. Now you can see that. Go through this and check all the possible combinations. Then what happens is after that location gets over, in all the locations it is filled with 0. You can see that. Then it generates here. Okay, then again it comes to 0. So again from 190 to 255 it is 0. Then again after 130 the value comes here. See here 131, 131, 130, 130. So then after reaching 255 again it will come back to 0. It is come back to 0. So that is the simulation process. So we have checked that now. We can close this. Now continue with synthesis. So click analysis and synthesis and say start. So now once it is 100 percentage, you can see the number of logic elements, which is 945, then number of registers, and then pins. You can see how many number of memory bits. Go to tools, netlist viewers, then technology map viewer, post mapping. You can see that this is our memory. Okay. You expand the analysis and synthesis portion. Go to resource usage summary. 4 input functions, 3 input functions, 2 input functions, and you can also see how many number of registers and how many memory blocks it has taken. All those things we can see, and then you can also see the RAM summary. The RAM summary shows that the simple dual port and then port A width, etc. Okay, so this information is also taken into account now. Okay, then we can continue with fitter. Okay, now when you do fitter, you can say that it shows how many number of logic elements and how many number of memory bits that we can see. But expand the fitter and go to resource section, go to resource usage summary. You can see 4 input function, 3 input functions, 2 input functions. Combinational with no register, register only, combinational with a register. All those things we can see. Then you can see the memory block, M9K block. Go to tools and then go to chip planner. So this is the place where your resources are sitting. And you can see all our memory block. These are all memory blocks. So 1, 2, 3, 4, 5, 6, 7. These 7 memory blocks are used now. So now we can generate the assembler. Okay, now how do we know that the design which works, right? Now we need to ensure that it is correctly working on the board. Now we have seen the behavioral simulation, but we also need to check whether it is working on the board. That's what we need to connect the debugger, which is called as the signal tap logic analyzer. So it is working here. Let us see that. Okay. Now first we'll connect the board. I will just show that information to you now. So we need to do programming. So first go to tools and then netlist viewers that we have seen already. Go to programmer. So tools programmer, and you can see there is an SYO file ready. Then what we can do is we can program the design. So just click start. So it shows 100% successful. Okay, so now what we can do is we can see the output, whether the memory values are correct or not, that we have to check. So that we can minimize here. Go to tools and then go to signal tap logic analyzer. So now you can see the data which is available down the memory data that you can see. This is the data out. When you expand this data out, you can see the locations are filled with 0, right? And then if you go forward, you can see 114, 113, you can see that. It goes till those values. 97, 94, 89, 85, 78, 71, right? And then again it goes to 0. So after reaching 68, it is 0. Because what is specified in that file when you say, you have to see that what is the memory value. So that we can cross verify here. So 0 to 63, it is 322. Then 64 to 126, it is 66. But 192 to 255, it is 0. So that's what we are trying to see here. So when you open this, when it is 192 to 255, any value you take here. Okay, 192, this is 253, this is 252. So 253, 252, if you see the value is 0. So 192 to 255, Any value you take, it is 0. That's what I'm just scrolling. You can see here it is 251, output is 0. 250, output is 0. So just go till 192. We'll scroll down and reach 192. Once the address reaches 192, what happens? Let us see that. So just scroll slowly so that what is the read value? Let us see. I'm just pushing it now. So it has reached 225 now. Still will move it and then reach 192. Right? There are chances that if you scroll more, you will still come to know what are the other values. Okay, now you can see this is 198, 197. Still it is 0. Slowly let us push that. 197, 196, 195, 194, then 193, 192. Once it crosses that 193, this still it is 0. But when it goes to 192, it becomes 260. So you can open that. Now you can see that this is the specific hexadecimal value. So now you can see 192. Till that only it is here. Okay, we can see these values in hexadecimal. We can also see these values in decimal. That's what it shows now. So the values are available here. Now you can scroll down. See, it generates. So we can see that in the signal tap logic analyzer, which is a useful debug tool, which you can use it. So what is the logic is, we can ensure that the design works on the board. Okay, that means you can see the value in the LEDs, that what value it is displaying in the memory. Another important thing is we can also see that on the signal tap logic analyzer. Okay. And there is one more tool which will help you to see the output, which is called as the in-system memory content editor. So once the JTAG is connected, you can see the instances and then connect it. So for example, you need to ensure that this particular process is running. So then we can generate it. So we can open the signal tap logic analyzer to cross verify the output here. So in all the first locations, it is 0. Then you can see the output. So this is your up counter value, and this is your down counter value, and this is your data out. So we can close this. Right, you don't need to save any changes. We can just close that again. Let us do timing analysis to check are there any timing constraints applied for this design. Go to tools and then go to timing analyzer. Create the timing netlist and see any clocks are there in the design. So there is only one clock. Let us check the timing. You click setup and then say report. You can see there are multiple paths and you can see the slack value. So go to locate path, locate in technology map view. So this is the launch flip-flop. It goes through combo logic and then it reaches the capture flip-flop. So this is the launch to capture. So this is the path. This is a critical path. And you wanted to see that path in the uh, technology map viewer that we have seen, and the same path can be seen in the chip plan. If we zoom, we can see that path. Right. So this is the path. This is the launch, and it goes through these blue lines. You can see that. Okay. I can still zoom to get a better picture. So you can see here. So this is the path. So you can see it is highlighting when I click here. This yellow and this path, this path, this path. So it starts from here and then goes here. So this is the end, start to end. This is the- That's what is shown in the timing analysis. Okay, here if there are any unconstrained paths, that also you can see. Report unconstrained paths, you can see these paths are unconstrained, which we need to provide. Okay, right. Let us move on to the logic here. So if you see that, okay, these are the reference documentations which you can refer for the specific things. And we have seen what is an intellectual property in the earlier case. What is an IP? They are pre-designed, they are pre-tested, and then they are pre-verified. What is a soft IP? We know, right? Like a NIAS2 software processor, which is available as an RTL, and it is going to use the FPGA resources. And then we also have discussed about the hardcore processor. Then what is an SoC FPGA? Because as per our sessions today, when it is an SoC FPGA, it has both processor as well as FPGA. Both are present into the same device. Then what kinds of processors are available in Intel FPGAs? When you say, there are two things you can answer. One, what kind of processor? When you say, it can be hardcore and softcore. That is one way of writing. What kinds of processors? When you say, even in the hardcore, if it is a Cyclone and ARIA devices, you have a dual core ARM Cortex A9. Whereas when it is the statics or Agilex, then you have a quad core application processor A53. So that information can also be added. So these are the things which you could refer. So that's what we have planned. So you can get an input on how do we started with the Intel SoC FPGAs and then we clubbed it. So to give a quick recap, you can see this information like how did we started. We started with the platform designer flow. We completed the platform designer. We instantiated that in the project. We performed analysis and elaboration. We compiled the project and then we implemented the design onto the board. While implementing the design onto the board, I also showed you how it works on the board. That means we have seen that how that works on the logic analyzer. Right. So I'll stop presenting. If there are any questions, please let me know. Are there any questions from your side? Please let me know. Okay, if there are no questions, thank you very much. We'll sync up again in the next class.